Okay, we've just got a couple lectures left here this semester, and even though we've already had the final exam, at least the written part of it, I would encourage you to watch these final two videos, the final two lectures, because this is an introduction to C++, which you're going to be using next semester. And a couple quick things about that, and then we'll kind of dig into it here. But C++, how it's distinguished from C. Now, C is a procedural language, and a procedural language, also sometimes called an imperative language, that means they're centered around procedures that do things to data. Or in other words, you have functions in C. Those are the key building block to all of our C programs. You write functions. Even where the program starts is a special function called main. And then you have data that's in the form of variables that you declare, arrays that you declare variables to. Even if you do dynamic allocation using like malloc or calloc, you store the reference to that or the address of that in a pointer variable. So it's all stuff in memory being operated upon by functions that are composed of various commands that are part of the language, or operators that are part of the language. Now, the good part about procedural languages and the good part about C is it's really fast. And the reason it's fast, one of the reasons it's fast, it's very close to the computer system's architecture itself, meaning that you have in the computer architecture of a typical computer system, you have memory. That's kind of like the data and the variables. And then you have a processor, which is kind of like the different functions and operators of the language that are then grouped into functions that then tell the processor what to do to the data. And that's also, procedural languages are great where we need control over that computer system. In other words, we need control of the CPU, what it's doing with the hardware, what it's doing to the memory. And it's also great where we need high performance because it's really close to the way the computer works. It's kind of a one-to-one relationship with here's this line of code, here's what happens to the memory, and the CPU is the thing doing all the work. Now, the bad part about procedural language, and specifically C, is that if you have a really large, highly complex program, you have a lot of functions and you have a lot of data. So you have both tons of functions, tons of data. And since the way that you need to write that code is to have those functions manipulate that data, a lot of times developers will resort to having a lot of global variables to give convenient access to that data. And the problem with that is now you have a collection of functions that access that global data and a whole bunch of that global data sitting around. So it's possible to have a function use the wrong data if the programmer isn't careful, or it's possible to have the wrong data passed to the wrong function, and so forth. And so the only thing that ties the right data together to the right function is the way that the programmer wrote the code. So the code is the only thing that ties those two things together. And that can prove problematic because we're relying on the programmer to make sure they're using the correct data with the correct function in the correct way, in the correct order. And that can be, by just leaving it up to the way the code is written, that opens the door to the possibility of misuse. And so also the low-level nature may prove problematic in C, where it trusts the programmer. So walking off the end of an array, a lot of you did that in the Game of Life lab and other labs. So you have to have a programmer who's careful not to go off the end of an array and into other parts of data. Now, that brings us to the introduction of C++. And C++ is actually an entire different language that basically adds some object-oriented functionality and some other changes to C language. So it's based upon C, but it adds things to that. And in fact, C++ is a superset of C, meaning that all the stuff we've learned in C still works in C++. C++ is a superset. So if you were to look at a Venn diagram, you have C in the middle, and then surrounding that is C++, where we've added some additional stuff for object-oriented programming and some other related things to it. So the new features are centered around creating and using objects. The objects encapsulate both data and functions, meaning that the inside of an object, you're going to have attribute variables. You're going to have methods, which are kind of like object functions. So you have both object data and object functions. And that allows us to do what's called encapsulation. So a particular object encapsulates both the data that it uses that belongs to that object and the methods or the functions that go with that data. And so that allows us to have multiple layers of organization. So unlike in C, where you either have a local variable or you have a file level variable, you have a global variable, and large projects end up with lots of global variables, and then therefore a way to kind of misuse those accidentally or purposefully maybe. But you'll notice that with encapsulation, if we stick certain variables inside of an object, and we make them private, then they're contained and they're controlled. Or even if we make them public, they still belong with that object. The code of that object, the methods can only access or will only access the things from that, variables from that object. And so it makes it so it's much harder to misuse things. There are a lot more layers we can create of organization and control. And because we've defined those objects that way, it reduces the chances for improper use. It minimizes that if we design our program properly, because we have a lot of shades of or a lot of layers of abstraction we can use to organize things. Now, classes are used to create objects. Those are the blueprints for object creation. And classes allow for both private and public data and private and public functions. So it gives us the ability to restrict these functions can only be called in this area. This data can only be accessed by these functions and so forth. And so what we're going to do is we're going to be looking at the C++ a little more carefully in today's lecture in an introductory way. Okay, so digging in, a C++ has the ability, it still has, remember, it has everything that C has. So you can still make functions just like you could in C. You can still declare variables just like you did in C. You can still declare global variables and local variables and static file level variables. So everything that you could do in C you can still do, but we've added on this concept of classes. So C++ class is defined in a similar way to structures in C, but unlike a structure, you can have both data and functions. So a class has to be defined before it can be used to create objects, just like a structure in C has to be defined before you can create structure variables from that or declare structure variables from that. So here's an example of a simple class declaration, and the stupid word processor likes to capitalize things inappropriately. So let me fix that. So here's an example class rectangle. So just like you would say struct and then provide the name of the structure, we do the same thing. So here the word class replaces the word struct, and then here we're putting the attributes that we want inside of that, the class variables inside of that. So this class rectangle has 4 attributes. They're all floats. ULX stands for upper left X, upper left Y. So that's the top left corner of the rectangle, and then it has a width and it has a height. And this is just an example that we're doing. So this is a simple class definition for a rectangle object. And notice that that could have been done with a struct because this is all data. We didn't put any methods or any functions inside there. So let's add some functions to it. So to add some functions to it, you would list those inside here as well. And essentially what we're putting inside of here, those are like the top things, these floats. Those are essentially the attributes, the data elements, the variables, the class variables, or object variables, I guess we would call them. And then we have the methods or the functions that are declared here as well. Now these are like, the only thing that goes in here typically would be like the function prototypes. We're going to have to write the code for those, the implementation code elsewhere. But the class, this is saying we're creating a class. Let me fix the stupid capitalization problem again. So what we're saying here is we're creating a class called rectangle. It has two floats, upper left x, upper left y, two more floats, width and height. And then it's going to have a function or a method called set position that accepts two floats, a function called, or a method called set dimensions, which we pass two floats to it, one called get area that returns the area as a float, one called get perimeter that returns the perimeter as a float. So the code we're going to have to write somewhere else, but this is defining what that object is going to look like. 4 floats and 4 methods. Now, one thing that's important to note is that by default, all of the object attributes and methods are private by default. So in other words, if we were to do this class, define this class this way, the way we have it here, nothing outside of this object could access any of these methods or any of these because they default to private. And so we have to make them public to make them accessible. So before this can be used, we got to do one more thing to it. So let's continue on here. We need to make them public. And to make those things public, we basically just put this public keyword with a colon in front of it, and everything after that now becomes public inside of that class that we made. Now, one quick thing here, that those sections can be either public or private, so we can actually set those ourselves. And here, I'm going to pause this for a second. I'm going to fix all these things where the capitalization is wrong, so we don't have to do that on every one of these pages. I'll be right back. Hold on one second. Okay, I jumped ahead and fixed a couple of those, so I don't have to keep interrupting the thing. Let me resume the presentation here. Okay, so notice that we can have a section that's either labeled as public or private, and sections can be any number or order. So I could have public, list some variables, private, list some variables or methods, public again, private again. But generally, the way that it's set up is public is listed first, followed by private with one of each section. So generally, you only have 2 sections, public section, private section, with here's the public facing things, the things that are visible from outside the class. Here are the things that are private that are stored inside of it. And you just have those 2 sections. But really, you could list each variable individually as public float ULX, public float ULY, public float width, and then you could switch to private and have some things private and some other things public. But that can be confusing, so by convention, it's done this way. Also by convention, I'm going to quickly mention is that class names are generally capitalized here to distinguish them from variables which do not start with capital letters. One other thing is if it's unspecified, again, if you leave off public or private, or you have variables that are declared outside of a public or private section, the default is private. And the answer might be like, well, why? Why is the default private? And the answer to that is because private is more restrictive and more secure than public. So it's kind of like, what's the default state of your car when it's in the parking lot? Should probably be locked. If you want to unlock your car and make it public so people can hang out in it, then you need to explicitly do that. So the default state is to be more secure rather than less secure. And that's so that you explicitly have to make something public to make it accessible outside of the object. Things that are not in a section that's declared public, default to private. Okay, so now we have this rectangle class, but we haven't written any of the implementation code yet. So our rectangle class right now looks like this. It's got these 4 floats. It's got these 4 function prototypes in here. Now we need to write some of the code for those methods. So how do we do that? Well, those are going to be outside of the class itself. So the class is defining kind of the template for what we have, including those function prototypes. Now we need the implementation code. And those look a lot like other functions that we would implement in our code or in C. But there's one key difference here. The key difference is how we name them. That here we have the name of the class and then colon, colon, and then the name of the method. So this looks just, other than that, it looks just like any other function definition that we would have in C. The only difference is the name. And what this is saying we're making the implementation code for the set position method of the rectangle class. So what we're saying here with this : is, hey, go into the rectangle class, : and then inside of that, this is the code for the set position method of that class. And we would do the same thing for get area. We would do the same thing for get perimeter and set dimensions. And one other thing to note is inside of here, X and Y are local kind of attribute or not attribute, local argument variables or parameters. But notice ULX and ULY, those are not declared inside of this function anywhere. Those are class variables. Those are attributes. And notice that we don't need to explicitly put, like if you're used to Python, you'd have self.ulx, self.uly. We don't need to do that. We could just say ULX and ULY, and that will access the attribute variables automatically by their names. Same thing down here with width and height. So those are object attribute variables. Those get accessed automatically. And then you'll notice that we would write the code for get perimeter and set dimensions similar to the way we did these. So once we have all 4 of those done, we would now have both the class definition and the implementation code for all of the methods of that class done. And now we would be complete. Now, to make an object instance from a class, once we have the class defined, it works just like any other type that you're used to in C. Just like you would have float speed makes a floating point type. Int score makes an integer type. Now that we've defined this rectangle class, we can now use it and say rectangle. Again, that's the name of our class that we had over here. Now that we have one, we can make a rectangle variable called R1. And to access the elements of that, it's similar to accessing the elements of a structure, r1.x, give it a value. r1.y, give it a value. If we want to call the set position method, r1.setPosition, pass the values into that we want to pass into that function, that object function. We want to call the get area function on rectangle 1, r1.getArea. And that will return that as a float because that's the way we defined the get area function. So again, similar to how structures work, but with the ability to have these methods as part of those objects. Now, because classes work as types, we can make arrays of the object instances. You can make pointers to object instances. You can get the address of object instances and store them in the pointers. And then if we're going to access the attributes or the methods of that through that pointer, we use the arrow operator instead of a dot. Again, very similar to structures, but it's like structures that can have methods inside of them. And classes behave just like any other type that we'll see in the language, including making arrays of them, passing them to functions, having functions return them. Think of it as you can do anything with those classes. You can do with types or with structs, or any other type really, but think of it as a structure that can have methods inside of it. Now, a couple quick things about coding conventions for writing the code for object-oriented programming like this in C++ is that class declarations are usually stored in a .h file. So that part that says class has the list of the attributes and the list of the methods, the headers, or the function prototypes for the methods, all of those will go in like a rectangle.h. Now, some programmers will use HPP instead of .h, meaning that a .hpp file is a kind of like a header for a C++ code, but more often than not, you'll see just a .h being used for the class declarations. The function implementations, however, are usually stored in a CPP file of the same name, so rectangle.cpp. So in other words, looking at this code we had back here, these things would be stored in the .cpp file, rectangle.cpp. These things back here, this class definition here, would be stored in the rectangle.h. And the idea behind that is that any code that wants to now use this rectangle class just has to include rectangle.h. And then the CPP file, if we add it to our project, the compiler will compile it and link it when we build that project. And that way, if we have used the rectangle class in other source files, it's very easy to just include rectangle.h and then create object instances of that inside of there and pass things to it and get things from that. And if we put the implementation code along with that, we included that all in the header file, we compile it, we get the compiler would complain, hey, you got 2 versions of the same functions that you're compiling. So this is the typical convention for that. You can define it all in one file. You in fact can define a class and the implementation functions for multiple classes in different or in one file if you want to. But it's typical to divide it up into its own source file like we have here, or like I describe here. And Java forces you to do that. If you're ever programmed in Java, Java forces you to put every object in its own source file. In C++, it doesn't force you to do that, but the convention is to do that because it makes it easier to reuse those objects in other code. Now, so you're free to do something different, but by convention, that's generally the way that you want to go about that. Okay, now you can also implement what are called inline methods. And inline methods mean that class methods can have the implementation code right in the class definition, but that makes those functions what are called inline functions. And that means that instead of being called like a function where the CPU jumps to some code somewhere in memory, runs that code, and then returns from that, what happens is the code of that is kind of like cut and pasted in directly in when the code where the function call gets replaced by the actual code. And that can make execution of those methods faster, but it can also bloat the size of your code, especially if you have a larger complex function. So you might want to do that with really simple methods, but you don't generally want to do that with larger complex methods. But notice that C++ gives us the option to do one or the other. All right, I'm going to pause for just a second, and I'll be right back, and we'll finish this up. Okay, so we talked about inline methods, and essentially the way you would do an inline method is you just, rather than putting the prototype for the method inside the class only and then defining the implementation outside that, you can put the whole thing right there inside that. But that does make it inline, so you don't want to do that with really large or really complex methods, because let's say you called that method 50 different places, that's 50 times that code has to get stuck into there. It can really bloat your executable. But for simple things, it can actually make things much faster because you're not having the CPU jump somewhere else and then jump back. You're just executing the code. Okay, so another thing that C++ has that you cannot have in C, and that's default attribute values. And this actually works for not just here, hold on one second. It works not just for we'll get to that later for default parameter values, default attribute values. So when you create a rectangle like this and you say rectangle R1, just like any other variable in C, that's going to have the values be just random garbage data. It does not clear them to 0. It does not initialize them to anything. It's just random garbage data. Just like if you make an integer I and you don't initialize it, it has random garbage data, whatever happened to be in memory in the area that is allocated to this. So the same thing is true. So if I say rectangle R1 and then I get the area of that, R1 is going to have some random area. It could be 0. It could be 1. It could be anything. It's just going to be a random garbage data rectangle. So if we want to create instances that have default attribute values, in other words, every time we create it, it's initialized automatically for us, then we need to create a constructor. So let's look at how to create a constructor. And if you're used to other object-oriented languages, like let's say Python, the constructor is called underscore init underscore. So in other words, it has that special name. C++ has the same concept, but the name of the constructor function is actually the same as the name of the class. So in other words, if I have a class called rectangle and it has a method called rectangle, that's the constructor. And then we write the code for that. So in this case, notice the constructor for rectangle just sets the upper left x, upper left y, the height, and the width. It basically just sets them all to be 0 in this case. So that way I don't have to get random garbage variables, attributes when I create one of these. I'll always get 0. And this will get called automatically. So the constructor will be automatically called when the instance is created, or when n instance is created. So any instance now I create of rectangle, it's it's going to run this code automatically for me. The constructor also has to be declared in a public section, and that makes sense that the constructor, if it's private, it could not be called externally, so it has to be in a public code section like we have here. The constructor must not have a return type because it's not really being called from anywhere, it's just being called automatically, so it doesn't have any return type at all, not even void, not int, not float. Doesn't make any sense to have that, so this is just blank in front of the constructor. And the constructors can have parameters passed and can be overloaded. In other words, you could have a constructor that we pass things to say how we want that object created. Just like if you're used to Python with the underscore underscore init underscore underscore method, you can pass things to that. The same thing is true in C++, and you can overload these, meaning you can have multiple implementations, some which have nothing passed to them, some which you pass things to. You have different ways of calling that constructor. And we're going to look at passing things to the constructor a little bit later on. Okay, there's also a special function called the destructor, which runs automatically when an object instance gets destroyed or unallocated. So in this case, the way that the destructor works, it has the same name as the class, but we have a tilde on the front of it. And then when we create the code for it, rectangle, colon, colon, tilde, rectangle, that's defining the destructor code. And a lot of times the destructors are used to, like, when we create some sort of object instance, if it allocates memory, a lot of times it'll be used to free up the memory, or maybe if the object instance opens a file, it'll be used to close the file, or if it opens some other resource or allocates some other resource, the destructor is used for kind of freeing that. And that can be really useful for preventing memory leaks, because the destructor, since it runs automatically when the object is destroyed, we don't have to call it. So if we create an object and it allocates things, as soon as that object is destroyed, whether it's because it goes out of scope, or whether we delete that object and get rid of it, or somehow destroy the object, that code gets free, or that destructor will run automatically, which will automatically free things. But we still would have to write the code in here that unallocates the things that were allocated. The destructor will run automatically, though. Now, speaking of dynamic allocation of objects, there's another way to create things rather than using malloc and free like we did with C. You can use malloc to create object arrays or arrays of object space. You can use free to free those, but there's a preferred way to do that in C++, and they did that by adding two new keywords. One of them is new, the other one is delete, and those don't exist in C. Those are something that are two new keywords that are specifically C++ keywords. So here's an example of that. So rectangle pointer RPTO. So we have a thing that can hold an address of a rectangle, and then up here we can set that pointer equal to a new rectangle. So notice, rather than using malloc and having to pass things in, where do we pass in the size, and we have to cast the void pointer to the right type when it returns from that, we can just say, hey, make a new rectangle, and that'll create a new one of those. And it'll set this address equal to that new one. You can also use this to make arrays of objects. So you could say new rectangle, square bracket 100 there, and it'll create a new block of 100 rectangles and set this pointer equal to that. And when we're done using that and we want to free it, we can just say, hey, delete that rectangle that was created up there. So two new keywords, new, creates a new instance, delete, deletes that instance. So think of it like new, kind of like malloc, but unlike malloc, it would call the constructor. And think of delete like free, but unlike free, delete will call the destructor automatically. And this is much cleaner than using malloc and free. So this is preferred for C++ objects. Also, a little bit more of the constructor. Arguments can be passed to the constructor. We mentioned that earlier. Let's look at how we would do that. So here would be the implementation for the constructor, where we pass in the x, the y, the width, and the height. And notice we just would set those like that. And then when we call it, to call the version of this that actually has those four floats passed to it, rectangle, rect1, pass in the things that we want to be. So this is creating a rectangle that has the x of 0, y of 0, width of 10, height of 15. And notice that also works if we're using the new keyword to create a new rectangle, we can actually pass the things in that way and then store those like that as well. So we can call, now if I were to just say rectangle and say rect1 without putting the stuff here, it would call the default constructor, which is void. So, and that's where overloading comes in. So I could have two constructors, one that accepts 4 floats, one that accepts just void that sets them all to 0. And the compiler will figure out which one is which based on the usage of how we're calling that. Now, default argument values, this is another thing that is unique to C++ that we didn't have in C. In C, you cannot have default parameter values. In C++, you can define functions, which includes methods in the constructor, to have default values for the parameters that are passed. So the default values are specified in the function prototype. Fix the typo here. So here's a class rectangle. Inside of the public section, we would have this. In this case, this is the constructor. It's the same name as the class, so that's the constructor. But notice I can say float x and say the default value is 0, float y, default value is 0, float width, default value is 1. Could make that 0, make it whatever we want. Float h, default value is 1. So that way, when the default constructor, when I would call this with no arguments, it would adopt values of 0, 0, 1, 1 for those 4 things. If I call it with arguments, it'll override these default values and put the argument I specified in. If I specified just 2, then it would use the defaults for these ones, but override the first 2. So it's positional based. It'll use the default. If we don't provide the argument, it'll use the value of the default that's in the prototype if they're not provided. Okay, overloading functions. C++ allows any function to be overloaded. And basically what overloading means is it means you can use the same name for more than one function. And that includes methods in the constructor as well. To be overloaded, the functions have to share the same name. So I could make 2 functions. For example, I could make a function called print. And I could have a version that I pass an integer to it. I could have a version I pass a character pointer or a string to it. I can make a version that I pass a float to it. I can make a version that I pass 2 ints to it. So I can make different versions of that same function that have the same name. But in order for the compiler to figure out which one you actually want, we have to have a distinct argument list, meaning the number of arguments has to be different, or the types of those arguments has to be distinctly different. So in other words, I could not have 2 functions of the same name called print that both just had a single int. It wouldn't work. But it will work if they have one that's an int, one that's a character pointer. The compiler will figure out which type we're trying to pass, or which number of arguments we're trying to pass, or which number of arguments of which types we're trying to pass, and it'll use the correct version of that function. So any function in C++ can be overloaded, which means that object methods can be overloaded, means the constructor, being one of those methods, can be overloaded. One thing that you cannot do, though, is you cannot overload the destructor. Ever. It just doesn't make any sense. So why doesn't it make sense? Well, the destructor gets called automatically, and it doesn't have any arguments that are passed to it, so there'd be no way to overload it because you can never call it explicitly. It happens automatically. So there's only ever one destructor because you're not in control of what gets passed to it or the arguments or what they look like. It just happens automatically when you destroy an object. So everything else, though, every function in C++ could be potentially overloaded. Now, returning back to this concept of classes as types. And this is actually somewhat important, that classes as types, that they work just like any other type. So think of like an int. You can make integer variables, int I, int j. You can declare pointers, int star or asterisk, IPTR, PTR. You can declare arrays of them, but notice you can do that with instances as well. You can declare instance variables, rectangle R1, R2. You can declare pointer variables, pointers to rectangles, rectangle pointer, RPTR1 equal address of R1. Just like with integers, you can declare arrays of them, rectangle rect array 1,000. So this is a space for 1,000 rectangle instances. You can have, they can be passed to functions, render rect, and here's a rectangle as a type of what we're passing. So we're passing to the renderRect function a rectangle object. And functions can return objects. So here, notice the return type is a rectangle of this compute collision rectangle. And we pass 2 rectangles to that. And I should probably, here, let me fix this. This should be R1 and R2 here probably. So notice we're passing 2 rectangles and it's returning the rectangle where how they overlap. So very similar to integers. You could pass 2 integers to a function, have it return an integer. You could pass 2 rectangles to a function, have it return a rectangle. Now, C++ supports several ways of passing things to functions, 2 of which we've seen before in C, and it works just like it did in C. Again, C++ is a superset, but there's 2 new methods I'm going to look at today as well. So let's take a look at each one of these in detail. The first one is pass by value. So pass by value works just like it did in C, that we basically just put the type of the object here in I, rectangle R. And then inside of the function, we would access it, and it would not change the original. In other words, when I pass by value, it makes an entire copy of that, and that entire copy of that object gets now, if I change it in here, it does not get changed in the original. So that isolates the original from changes made to that variable inside of here. But in order to do that, it has to make a copy of the entire object that's being passed and copy it into this new variable that's in here. And that making that copy does take CPU time, especially if it's a large object. That can end up being costly. Could end up slowing your program down. Which brings us to the second thing that we talked about also in C, and that's pass by pointer. I can pass the address of something and then have a pointer inside there get it. So just like function is accepting a rectangle pointer. And we access it through the pointer. We use the arrow operator instead of the dot operator. But this change is now going to affect the original. Since we pass the address of that rectangle, any changes we make to that rectangle are happening to the original. So only the address is passed. The changes are going to affect the original. And when you call that function, we have to explicitly pass the address of that object. Put the ampersand in front of that because this is expecting an address of a rectangle. So we have to give it the address of a rectangle. And that's also used when we pass arrays of objects to functions, just like the same thing in C that you're used to. And you can pass in a null pointer if you want to say, I'm not passing anything for this parameter. Now, that brings us to 2 of the new ones here, pass by reference. C++ has the ability to have it pass the reference automatically and do all the dereferencing automatically. Now, in this case, the way we would declare that function is we put this ampersand here. But the ampersand here in the parameter list does not mean address of in the function definition. This means the reference is of this, whatever object is being used. And we can access this inside of here just like we would if it were a local variable. But it's actually changing the original one. So only a reference is passed. And references are really behind the scenes the same as addresses. But the difference here is the compiler is going to do some of the work for us. In other words, when we call the function, we don't have to explicitly put the ampersand to pass the address. It does it automatically. The second thing about this is that we don't need to dereference it inside of the function in order to access it. It's done automatically. The compiler does that for us. So it's similar to pass by pointer, but null references aren't allowed. It's also not thread safe. Let's not worry about that right now. And all of the dereferencing and all of the, actually the add ampersand part here, all that's done by the compiler automatically. Now, I'm not a fan of that. I actually don't like this feature of C++. I think that since this can do the same kind of thing, but you explicitly have to pass the address, that's more clear in the code. I can tell when in this function call, hey, this function f1 is getting the address of this rectangle. It could be changing that. But looking at this one, when you call it f1, you're passing a rectangle. This function could be changing that object, and we can't tell by looking at that function call. And I think that that's it's doing some mysterious behavior that I'm not, as a programmer looking at the code, I cannot tell looking at that. So I'm not a huge fan of the pass by reference. It does make stuff faster. It can make stuff more efficient. It can make the code look like you're referencing a local variable when you're really referencing the variable that's outside of that you have a reference to. But it also, because it's doing that stuff automatically behind the scenes and the compiler is doing that for us, we as a programmer can't immediately tell by looking at the code that that's what's happening without looking at the function to notice that it's a reference that it has. All right, the fourth and final one we're going to talk about today is passing by what's called a constant reference or const reference. And notice that looks just like the pass by reference, but we added the word const here. And remember, the pass by reference changes here affect the original. If we pass by const reference, we're telling the compiler, don't let them change this inside of here. Don't let them change this. This is a constant reference. Don't let them change things that's referred to. So this would not be allowed because we declared it as a constant reference. There's another typo. Let me fix that. Correct. So an object reference is passed, but it doesn't allow changes to that object. It's safe, like pass by value, in that it won't allow us to change that object. It's safe, but it doesn't have the overhead of passing by value where it has to make a copy of the entire object. So in other words, we're still passing a reference to the object, which is fast and efficient, but we're telling the compiler, don't let this function make changes to that object. And that can actually be clear to somebody looking at this code that, hey, this thing is not allowing this is not going to allow it to be changed. And if you try to change that object in here, the compiler won't let it. Also, no need to dereference, just like pass by reference. Also, still not thread safe. All right, a few final things here. If you make a static attribute, in other words, notice in the public section we have this int count, but we put the word static on the front of that. Now what that does is inside of a class is that creates what's called a static attribute. And a static attribute essentially works just like these attributes, but it's only allocated once. And also, if we have a static attribute in our class, we also have to allocate it outside of that like this. So int static example class : count. So we have to declare that. And the reason for that is because this is just a blueprint. It's not actually allocating any memory. So we need to have a declaration, a variable declaration outside of that to give this thing application lifetime for that variable that's part of that class. But essentially, static attribute values have an application lifetime, and they're shared between all instances of the class, where these other non-static ones, each instance has its own. And so you'll notice that this is kind of, you can think of it kind of like a global that exists, but only for all members of that class. So in other words, this count, we could have the constructor increment it, we could have the destructor decrement it, and any of these objects could tell how many objects of that class type have been created. And there are some reasons why you might want to have that. It can be used as a way for kind of a shared variable that's shared between every one of the members of that class. So they're sharing that, but they have their own X and their own Y, but a shared count. So you can also make static methods, like a static method function where that code is shared between all of the things, but static methods can only call or access other static methods and other static attributes. They can't access instance attributes. All right, final thing today that we're going to talk about is object assignment. Object instances, just like structures, can be assigned to one another. So in other words, here I've created two rectangles, R1 and R2. I can perform, say, R1 equal R2, and that's going to copy the entire instance, including all the attribute values from R2, over the top of R1. So you can assign one object to another object without having to do some weird mem copy or something like that. We can just say R1 equal R2, and now we've made a copy of that. So in other words, R1's values will now get replaced with, will now be 100, 100, 20, 30, where they started out as 0, 0, 10, 20. So when performing an object assignment like that, all the member attributes are assigned during the copy automatically. So in other words, we don't have to say R1.x equal R2.x, R1.y equal R2.y, R3 or R1 dot width equal R2.width. We don't have to say all that. We can just say R1 equal R2. It'll copy the entire thing automatically. Okay, so that's our introduction to C++. Think of it like C language. Everything in C language still works, but we have classes. We have a couple other features as well. Pass by reference is new. The ability to overload functions is new. The ability to have default parameter values for functions is new. But other than those few things, it's like C with the ability to have classes added on. A class works a lot like a structure that has the ability to have functions or methods inside of it. And one other thing that was new is the ability to use new and delete rather than malloc and free. And that gives us the ability to do some dynamic allocation things without having to use something like malloc and realloc and calloc and free. And the advantage of using new and delete is the constructors will be automatically called and the destructor will be automatically called when we do delete. Okay, so that's it for today. Everybody stay safe. Again, be prepared for the programming portion of the final exam, which will be posted to the course site during final exam week. By next Tuesday before your class time starts, you'll have several days to get that in, but it will have a time limit once you start it. So try to block out a few 3-4 hours of time that you can work on that. You probably won't need all that if you're prepared. So I'd be prepared. What's the best way to prepare? Make sure you've done all of the labs. Make sure you've watched all the lectures. Make sure you look at the study guide outline and all the topics that are on there, and be ready to write some code. Okay, so that's it for now. Everybody stay safe.